So let's take a look now at an example that's not based on one proportion. We're looking at the question of whether tip percent has a linear relationship with the amount of a bill. So we figure most tips are somewhere between 10 and 20%. It seems like the tips get bigger when the bill gets bigger, but the real question is here, does the percent tip depend on the bill? We can think about this for a moment and come up with some explanations why it might and why it might not. You might see that like the cup of coffee effect, right? You buy a cup of coffee for $2. If someone actually brought you that coffee and waited on you at a counter or a table or something like that, you might tip, I don't know, 50 to 100% just because sometimes leaving less than $1 doesn't really seem right. So this would suggest that a smaller bill would have a larger tip percent. And this is kind of getting at a negative association, because this effect would go away once our bills start to get big enough that taking 10 to 15% is appropriate. On the other end of things, you might figure a very fine restaurant, so fine dining, people who are spending a lot of money anyway, they may not have a lot of financial struggles and they may just enjoy tipping more, right? So you might see some higher tips on larger bills, not just higher tips, but higher tip percents on larger bills just because your customers aren't really strapped for cash and they feel perfectly comfortable leaving a larger tip. And this might suggest a positive association. So we don't really know a priori which one we expect. And so we're going to go into this with just a neutral question of whether there is a linear relationship, positive or negative, we're not asking, between the amount of the bill and the percent tip. That means our null hypothesis is no linear relationship, and we measure linear relationship with slope or correlation. Realize we're talking about two quantitative variables here. So I could write these hypotheses in terms of either slope or correlation. I'll go ahead and do this in terms of correlation. Slope, if I were using slope, I would do beta. That's the parameter. For correlation, remember that that's the Greek letter rho. So my null hypothesis is that rho is equal to 0. Note that this is not a p. We're not talking about a proportion. My alternative hypothesis is that this correlation rho is not equal to 0. It's a two-sided alternative hypothesis because we didn't specify whether we're interested in a positive linear relationship or a negative linear relationship. So we're going to go ahead and create a randomization distribution in Statkey. We're going to go for test for slope correlation under randomization hypothesis tests. And this particular data set is in the drop-down menu. It's called Restaurant Tips, Tip Percent as Function of Bill from the drop-down data menu. And let's just go from there. So here we are in Statkey under randomization hypothesis tests. I'm coming all the way down to the bottom, test for slope correlation. And in this drop-down data menu, restaurant tips percent tip as function of bill is the one we want. Note that there are two that look very similar. Right now we're interested in percent tip. We can see from the original sample over here to the right that it looks like the correlation is very slightly positive, but not very strong. So we're not going to change our alternative hypothesis, of course. We can't do that after we look at the data. So we're going to go on with a two-sided test. Here we can see under original sample, our sample correlation R is equal to 0.135. We can also see that our null hypothesis is that rho is equal to 0. That matches our null hypothesis, and in fact, we can't change that like we could for a proportion. It doesn't really make sense to be testing against a null hypothesis of a correlation being anything other than 0, since the null hypothesis is generally that there's no association between these variables or that there is no effect here. So coming back to our tutorial, we have a sample correlation R of 0.135. Not a very strong correlation because it's fairly close to 0. Does there appear to be a strong linear relationship? I would say no, a very weak relationship, and it is positive. It's a weak positive association. Identify a few outliers. We want to see if we have any evidence that maybe our non-zero correlation is just due to one or two outliers. I can see that these 2 points up here are the biggest outliers. They don't seem to have a huge effect on that correlation. If anything, they're probably bringing it closer to 0 since they are so far away from that line, but they don't seem to be affecting the slope at all. So it seems reasonable that these outliers, even though we want to acknowledge that they're there, they don't have a very strong effect on the linear relationship. So those are, looking at those again, those are a bill of $20 and a tip of 41%, a bill of $24 and a tip of 42%. So this looks like maybe when mom and dad came in to eat, right? But no, they don't seem like they would have a very large effect on the correlation for the reasons that we indicated. We'll generate a few thousand samples. We will check the two-tail box because this is a two-sided alternative hypothesis. And then we will click on the endpoint value that is closer to our sample statistic. So let's see what we mean by that. I'm going to hit generate 1,000 samples a couple of times and click on two-tail. Now down here at the bottom, I see two values. I see 0.173 and negative 0.151. Let's see what happens if I overwrite the one that's further from my value. My sample statistic is 0.135, which is positive. It's closer to the positive value. Let's see what happens if I overwrite the wrong one. Just demonstrating. We can see the whole thing turns red. It's giving us two overlapping tails. So I want to back up and say, that's not really what I meant. Maybe we'll start over from the beginning because it gets confusing at that point. Two tails. Very important that I overwrite the 0.163 instead. It's going to then move the 0.163 over to where 0.135 is, and it's going to reflect it onto the other side. So I'll overwrite this with my sample statistic, and we can see that it moved in a little bit, and it gives us two tails, which is what we want. So our p-value is the sum of these two tails, 0.048 and 0.048. 0.048 times 2 gives me 0.096. That's my p-value. And now I want to interpret the p-value and make a formal statistical decision and then state my conclusion. Remember that when we interpret a p-value, what we're saying is if the null hypothesis is true, then the chance of observing a sample statistic like mine is equal to, or one that's more extreme, is equal to this p-value. So all I need to do is fill in a more descriptive version of if the null hypothesis is true, right? My null hypothesis is that there is no linear association, so let's go ahead and give that a try. So a few ways to say this, but this is a pretty straightforward way. If there is no linear association between bill and tip percent, our chance of observing this sample correlation or one more extreme is 9.6%, so close to 10%. Intuitively, that's not a really rare event. So it seems like this is not very strong evidence against the null hypothesis. Our formal statistical decision, we want to compare this p-value to 0.05, our given significance level. 0.096 is not less than 0.05, it's greater than 0.05, and that means we fail to reject. Fail starts with an F, fail to reject. The conclusion of the test in the context of this given significance level is that we do not have statistically significant evidence of a linear association between bill and tip percent. Okay, so because we were given a statistical significance level of 0.05, it's sufficient to just say we don't have statistically significant evidence. If we were not given a significance level here, right, if this part had been left out, we would just have to describe the strength of our evidence. And because we're very close to 0.1, we might call this weak to moderate evidence. Weak to moderate evidence still can be considered statistically significant if we were given a different value of alpha, right? It all depends on what the threshold was determined to be in advance. So there is weak to moderate evidence which can be considered statistically significant, but the definition of statistical significance for this particular application is the alpha that we were given. So we would say fail to reject, and we do not have statistically significant evidence.